So now we'll consider what an inflection point is. Now, an inflection point, by definition, is a Now, remember concavity refers to whether it's concave up or down. So if you have something like a parabola, and it kind of looks like that, is it concave up or down?
Up.
This is concave up. Is it ever concave down?
No.
No. This is concave up all the time.
Yes.
And in other words, there is no inflection point. So really, inflection points really happen with, cubics and above, if you're talking about polynomials. So if we take another example of a cubic, then, the stock standard cubic would be like this. And if we take a bit of analysis and we look at it, you might say it's concave up or down on the left.
Down.
And on the right?
Up.
And so this would be an inflection point. I could have other cubics that look like this. And you might say something along the lines of, maybe somewhere around here. You might see it as concave down on the left and concave up on the right. And that would therefore imply somewhere around there is an inflection point. Depending on what graph you've got, you might have something like this. And you might potentially, I'm not drawing it perfectly here, but just giving you guys the idea. You might potentially see something like this where you might go, well, that's concave up on the left. And this is concave up on the right. But in the middle, there's this section which is concave down. This is possible, which means that this will now have two inflection points here and here. So you can have, curves that don't have an inflection point. That's very possible. Cubics will have one, for example. And you could have, this might be a quartic, which will have two, and so forth. Those are all very possible. So remember what the definition of an inflection point is. An inflection point is a point where concavity changes. And also, depending on what textbooks you use and where it was published and so on, you might see it called an inflection point, which is what I'm going to call them. But you also might see it spelled as with an X. So instead of inflection like that, they might spell it as an inflection like this. Same thing, different word. It's kind of British US thing, doesn't really matter. You might see, instead of being called an inflection point or inflection point, you might see it being called point of inflection. And they're all, this confuses some students, but really, they're all the same thing. Slightly different terminology, if you consider them different, for exactly the same thing, which is a point where concavity changes. Make sense?
Yeah.
All right, now, how do you imagine we would find a inflection point? So if you think about it, an inflection point is where the concavity changes. So what could the concavity be? And actually, let's be even more specific. What do I mean? Like, perhaps you don't understand what I mean. What do I mean by where the concavity changes? Can we be more specific? So maybe my definition here wasn't clear enough, because a concavity could be changing but still remain concave up. So when I say a point where concavity changes, I mean a point where the concavity changes from concave up to concave down, or vice versa. So concavity could change in the sense that, you know, it's concave up to more concave up. We're not talking about that. An inflection point doesn't care about that. An inflection point only cares about when you go from concave up to concave down, or vice versa. So remember, concave up means what? What does concave up mean mathematically?
Second derivative is positive.
And what does concave down mean?
It's negative.
So if you want to go from concave up to concave down, or concave down to concave up, what do you think needs to happen?
Equals 0.
Right. So to find an inflection point, what you would need to do is let the second derivative equal to 0. Which of course means, you know, your first job is to firstly find the second derivative. All right? And that would give you some points, which you then may be able to solve for an inflection point. So if we take an example, like y equals x to the power of 4 minus 4x cubed plus 5, and assume that I'm only interested in the point of inflection, then I would say the first derivative is 4x cubed minus 12x squared. If I'm interested in stationary points, I would use the first derivative. But if I'm only interested in inflection points, then I will go for the second derivative, which will give me 12x squared minus 24x. And my job is to solve for this equal to 0. That hopefully should not be too difficult. You can factor out 12x, giving you x minus 2 equal to 0, leaving you with x equals 0 and x equals 2 as your possibilities. So now I've got two values of x where the second derivative is equal to 0. My next job, of course, as usual, is to find the points themselves. And therefore, I'll get my points. So if I sub in 0, basically, I'll get y equals 5. And I'm going to get negative 11. So at this point in time, I've got 2 points, 0, 5, and 2, negative 11. And this would appear to be my inflection points. And for this question, they probably are. All right? I've got 2 inflection points, and I've got their coordinates. Any questions with that so far?
No.
Now, to be honest, the vast majority of time, especially in SL, this is it, right? They won't kind of throw anything tricky at you, and these will be your inflection points. However, I mentioned before that I kind of need to be a bit more, I don't want to tell you the wrong thing. So all we've done here so far is that the second derivative equals 0, and I'm saying that these points are second derivative equals 0. But I want you to think about this. If the second derivative equals 0, does that mean we've got an inflection point?
Can you say that again?
So my question is, our second derivative equals 0. Does that mean we have an inflection point?
Yes.
All right. Do you both agree the answer to that is yes?
Yeah, I don't know.
All right. So let me tell you the answer. Clearly, I think you know where I'm heading with this. The answer is no. It doesn't mean that necessarily. That is the correct answer. But let us just take a look at, for example, y equals x to the power 4. Do you guys know what y equals x to the power 4 looks like?
Yes.
What does it look like? What does it look like roughly?
How do you want me to describe it?
Or would look like approximately?
It's like very parabola.
All right, so let's go with that. So it's technically not a parabola in the sense that it has to be power 2, but you know, that's the idea, right? It's some sort of concave up curve that kind of looks like this, right? And it'll go through 0, 0, and it'll go through 1, 1, and all the rest of it. All right, my question is, what happens at 0, 0, according to you? What type of point is that?
Turning point, minimum.
What? Right, it's a turning point and it's a minimum. We all agree with that, and that's quite clear to us, right? So now, let us imagine we didn't know that. And let us just do the calculus. So if y equals x power 4, y dash is 4x cubed. Y double dash is 12x squared. Now for y double dash equal to 0, that means x squared equals 0, which means x equals 0, which means y equals 0. So that means I've got 0, 0. And in fact, at 0, 0, I've got the second derivative equal to 0 at 0, 0. So the second derivative equals to 0. Does that mean I have an inflection point?
No.
No, it does not. So you can't say that just because your second derivative equals 0, that you have an inflection point. If you have an inflection point, and that's an if you have an inflection point, your second derivative must equal to 0. If you have a $2 coin, it has to be a coin. But you can't guarantee, without doing further steps, that just because your second derivative equals to 0, that it must be an inflection point. A second derivative equal to 0 means it's a potential inflection point. You need to still go further to prove that it is an inflection point. Now, those details might be best talked about next week, because those are fine details that I don't think will be a huge issue for you, especially in SL. But I just want to sort of raise the sort of red flag here. We have not proven it's an inflection point. We need to further prove that it is an inflection point. Because we might potentially, however unlikely in SL, you might potentially be in a situation where you've solved for the first derivative, for the second derivative equal to 0, but it is not an inflection point. So there are further steps that you can take to basically check all your so-called second derivative equals to 0 points to see if it is actually an inflection point. This point has a second derivative equal to 0, but it's concave up on the left and it's concave up on the right, and therefore by definition it is not an inflection point and should not be included in your answer if you're asked, you know, for inflection points. Does that make sense?
Yep.
Great.